Right in here. All right. So, topic here is this idea of filters. So basically I'm going to cover this. I posted the before lecture notes or whatever, and I'm going to cover those basically in this section and in the next. And I will go ahead and sort of proceed here. So the basic idea, so I derived, if you watch the other lectures, right? So I go through and basically have this Laplace impedance. It looks exactly like the impedance that we learned, except it's more general. It applies to any input. So basically, for a capacitor, it's 1 over SC. For an inductor, it's SL. And then for a resistor, it's just simply R. All right. So it's just what we're used to doing. Basically, what we do is you would analyze the circuit just like you would with regular impedances, and you use these Laplace impedances, right? So basically what you do is you look at this and you say you determine what the input and the output of the circuit are. The input's always some voltage or current source, and the output's always some voltage or current somewhere in the circuit, right? And so what we do is we figure out what is this relationship between an input and an output. We use our circuit rules to get the relationships in terms of the variable, and then we make this transfer function, which tells us the ratio of the output to the input. And it's always got to be a rational function of S. And this is what a rational function of S is. Basically, it's a function of polynomial. It's a ratio of 2 polynomials of S, right? In other words, can I ever have a 1 over S? No, right? It has to somehow be in terms of a polynomial. Polynomials have, S to the power of some positive integer. Okay? So it should always have that form. All right. So that's the basic approach we use to create the transfer function. And basically the way that I draw that sometimes is I say, okay, well, there's this transfer function h of s, and I have an input and an output. And basically what you do is you say, I've got the input transform, and then I have the output transform. And you take the input transform, multiply it by h of s to get the output transform. And then that I can inverse transform to figure out whatever the actual output is. Okay. All right. So here is an example circuit. Let's say what I want to do is I want to figure out if V of t is my input and V sub c of t is my output. Okay. I want to figure out what the transfer function would be from V of t to V sub c, right? Like I said, like I determined some voltage or current that's the output. In this case, V sub c is the output. So how do I approach this? How would I figure out how to get that transfer function? I want h of s is equal to V sub c of s over V of s, like that. How do I approach that?
I wouldn't find the equivalent impedance to get the voltage for the parallel combination.
Yep. All right. And so basically what you'd say is you want to turn this in and say the 2 microfarads and the 0.1 henries are in parallel with each other, right? So we should be able to simplify that somehow. So let's do that, right? If I simplify that down, what would it be? So I guess just in general, what we're saying is you would replace this. You'd say I've got V of t. All right, so here's V of t. I've got a resistor here, so I'll call that R. And then we're going to combine that into one impedance right here. I'll call that Z1. Right? That's basically what you're proposing to do, I think. All right, so at this point, isn't the voltage across that parallel combination, that's going to be the same thing, right? That's still V sub c, right? If I'm in the Laplace domain, though, I would actually say this is, I should label it this way. This is V of s, and this is V sub c of s, like that, right? So how do I approach this thing here now? How do I solve for V sub c of s for that circuit? Voltage division, yeah. So what would it be? V sub c of s is equal to what?
Yes.
Yep. So V of s times Z1 over R plus Z1. And the thing I got to do is figure out what Z1 is. Okay. So Z1 in this case is the parallel combination of those two things. So the way I would do this, I'd say it's 1 over SC in parallel with SL like that. Right. And so I got to figure out how to compute that. All right. So how do I do that? All right. This is the picture we have here. So 1 over, so Z1, this 1 over SC in parallel with SL. How do I write that out?
C plus 1 over SL to make it 1.
Yeah, you could, so yeah, you could do it that way, right? And so what I always remember that if I've got two impedances, I usually skip the step of writing it that way. And I usually say it's the product of them on top over the sum of them on the bottom. That doesn't apply if there's 3 of them. It doesn't work like that. It doesn't mean you take the product of the 3 and then the sum of the 3. If you had 2 impedances, what I just said, right? If I took 1 over the impedance plus 1 over the impedance, take that whole sum and do 1 over that, that's the right way to do it. If I have 2 of them, it simplifies to this. All right. Is this guy a rational function? All right. So how do I turn it into a rational function of S? Well, multiply by SC over SC, right? So multiply top and bottom by SC, right? So what does that turn this into?
S squared LP on top.
Not quite, right? So I got an SC times a 1 over SC. They're going to knock each other out, right? So I get an SL upstairs. On the downstairs, what do I get? 1 plus S squared LC. Like that. All right. That's a rational function. Now, what we said was that V sub C of S was V of S times this Z1 over R plus Z1. Okay. So now what do? Well, I got to plug in this Z1 into that expression, right? So what do? I say V sub C of S is V of S times SL over 1 plus S squared LC over what? R plus 1 over 1 plus S, not 1, SL over S squared LC. Okay. So that's clearly not a rational function either. It's an ugly looking guy, right? So what do I do with this? Yeah. Yeah. Multiply top and bottom by 1 plus S squared LC. There's a reason why we do this, right? So this is really no different than what we did with impedance, except I'm keeping it sort of symbolic because I'm keeping it as a function of S is really what I'm trying to do. All right, so if I do this, what happens when I do that multiplication? Right, well, let's look at the top, right? So I have 1 plus S squared LC times this SL over 1 plus S squared LC. What happens when I do that multiplication? Yeah, they cancel each other, right? What happens to the bottom? So I got V of S times SL on the top. What happens on the bottom? Yeah, these guys cancel, and then this times that, right? Yeah. So it basically becomes R plus SL plus R, or I should say it this way, S squared LCR like that. Okay. If I do that multiplication. And so normally if I say, okay, what's the transfer function here? Well, the transfer function is always output over input, ratio of the output over the input. So that would be the ratio would be V sub C of S over V of S. And the transfer function would basically be this thing, SL over S squared LCR plus SL plus R. On the homework, I think what I do is I in order to make sure that I can really check your answers, I constrain one of the points in this thing. I think I say this has to be 1. So if I told you in the homework that this coefficient has to be 1, but this is the answer you got, what would you do? Divide the top and bottom by R, right? And then you would get something that's equivalent. Right. I have to do that because there's infinitely many ways you could technically write this thing. So I have to constrain you in a particular way to be able to do it. All right, that's why I do that. All right. So that's my transfer function. Somehow this guy is a function of S. Now, why it's a function of S, we're going to see a little bit as we go, right? Because I want to analyze this thing. I called my lecture the filtering concept. Somehow I'm going to use this for the idea of what I call a filter. All right. So that's how I get the transfer function here. Now, the question is, what do I do with the transfer function? All right. And what I do with the transfer function, right, if I wanted to, I could say V sub C of S, right? V sub C of S is equal to H of S times V of S. Since these things are Laplace transforms, if I have the Laplace transform of the input, I multiply that by H of S, do the partial fractions and all that junk, and I get whatever I inverse transform whatever I get and turn that into something, right? That's the basic general approach. Now, again, we focus pretty heavily on sine waves, right? If I focus on sine waves and we're only about steady state, then I can make some approximations and make this easier and make it useful to me in some way, all right? So I did want to talk about something though here, because it's a concept we're going to talk a lot about, is this word, these two words we use, poles and zeros, right? In general, this H of S, I took an example here for 1 over SRC plus 1. This came from my favorite circuit, all right? The RC low pass filter, okay? What I say is this guy has a single pole. Right? I'm going to define this term, poles and zeros, right? So basically this is a function of S. I wrote this transfer function H of S. It's a function of S. And we say that in general, S is a complex number. So if it's a complex number, it has a real part and an imaginary part. So looking at this, so I said S equals sigma plus J omega. All right, that looks Greek. But what's the real part? What's the imaginary part of that expression? S is sigma plus J omega. So what's the real part? What's the imaginary part? Sigma is the real. What's the imaginary? Omega, not J omega, right? It's omega is the imaginary part, right? So if what you would do then, if I think about this, is H of S is actually a function that is, it's a function of a complex input, S. And so if I were to plot it, it would be 3-dimensional. And I'll have to make 2 plots, right? I'd have to make a plot of its magnitude and a plot of its angle, okay? And so if I plotted the magnitude of H of S, so what I'm saying is if I plot the magnitude of H of S, which is whatever the magnitude of this would be, I could basically, for all of the different possible values of S, which is basically anywhere in the complex plane, what I would do is I would see what this thing looks like, all right? So I took an example here and said, well, what happens if, I think for the way that I have this, what happens if I have, for this particular circuit, let's say I have this 1 over S times 0.01 plus 1, like that. Right? Let's say that was my transfer function. So for the value of R and C I had, let's say I had 1 over S times 0.01 plus 1. So let me write that, 0.01 S plus 1, okay? All right, now, what happens, looking at that function, that function potentially has some problems. Basically, I plug in S equal to sigma plus J omega, and I would evaluate this thing at every point on the complex plane, right? In other words, for every real and imaginary, right? I would evaluate this thing, right? Isn't there a problem at some values of S associated with that thing? What value of S would be a problem? Yeah, basically, if I look at the bottom of this, 0.01 S plus 1, if that were equal to 0, what's the problem with that being equal to 0? Yeah, I'm dividing by 0. Basically, the value of that thing, the magnitude of that thing would become infinite at that point, All right, so the value specifically is S equal to -10. Okay, so we call that point, basically what I did here is I made a plot of what that magnitude would look like. It's a three-dimensional plot because you're saying basically the S value has the real part and the imaginary part. And so at S equal to -10, what I see is this guy is basically exploding. His magnitude is headed off to infinity. If I moved away from that point, what I would see is that his magnitude would get smaller, right? At that point, it would basically be equal to infinity. So for that reason, what I say is the pole is any value of S that causes H of S to go to infinity. I call that a pole, all right? Now that turns out to be a useful thing for me in terms of this thing I'm calling filters, knowing what a pole is. And then any value that causes, or any value of S that causes H of S to be equal to 0, we call a 0, right? So if my transfer function, instead of this, if it had been, let's say, S over 0.01 S plus 1, where would that have a 0? What value of S would cause this H of S to be equal to 0? 0, all right? So what we do is we sometimes make what we call a pole 0 diagram. And I would say that at S equal to -10, this guy has a pole. So where is S equal to -10 on my, it's right over here. And I make an X to show that at that point, it's got an infinite value, all right? Now, this is basically looking at this from the top down. That's really what it is to say that basically there's a value that's kind of shooting out of the page if I look at the magnitude of this thing at that point. All right, now we're not going to get into complex functions and stuff like that, right? But this notion of what is a pole and what is a 0 is really important to us. I'm going to use those terms a lot, all right, from this point onward, about a pole and a 0. Question?
I think it's actually -100.
It is -100, yeah. Yeah, so you see, I mean, the important thing is it's the value, whatever value of S makes the denominator equal to 0. So in this case, apparently S equal to -100 will in fact do that. Okay. All right. So we're going to use that concept a little bit more as we go. So let's say I got this example here. All right. H of S is 3S over S plus 2 times S plus 4. This came from analyzing some function, right? All right, what do I do here with this? How many poles and how many zeros? So let's take a look at it. What values of S make this guy equal to 0?
One value.
One value does, and it's at S equal to 0. And I define that by saying it has to be right there at the origin. All right, and I make an O to denote a 0. Where are the poles? Yeah, basically I say wherever, so S plus 2 equal to 0 would be a problem. S plus 4 equal to 0 would be a problem. And so S equal to -2 and S equal to -4. So those values, S equal to -2, S equal to -4, there's -2, there's -4. All right, now all I'm doing is just defining this thing right now. Yeah, I'm going to come back to it because a pole has some meaning to me as I talk about filters, and a 0 has some meaning to me as I talk about filters. All right. So I want to be able to just define those things. All right. But in general, it's kind of a simple concept to think through. All right. So basically, what we've kind of learned here so far is basically what I'm going to do is I'm going to say I can define and make for myself this transfer function using a circuit analysis. I get that transfer function as a rational function of F. The ratio of two polynomials. To find the output, I basically would take the Laplace transform of the input, multiply the Laplace transform of the input times this thing, take the Laplace transform of that, and I would get my result. And my result in general, as I wrote here, is basically that when you take the inverse Laplace transform of that, you get the steady state output and the transient. So it covers everything all at once. All right, now again, we don't always care about that. All right, so in the lecture that I posted for Wednesday, I basically had this circuit again, right? And I said, all right, well, let's use that approach, right? So when I go through, I defined a transfer function, H of S is that thing up top, right? 1 over SRC plus 1. So V out of S is H of S times V of S in terms of if in terms of these inputs here, so V in, I should call that V in, right, like that. All right, what I did was I wrote here, if my V in is this function, it's a cosine. This is the Laplace transform of cosine. All right, you probably saw that in differential equations. All right, I don't necessarily expect that you remember it. All right, but that's what its Laplace transform is. So if I use this approach, I would say, all right, well, the Laplace transform of the output is equal to h of s times v in of s. So I wrote that down here. Here's h of s, right? Here's v in of s. Put them together. Okay. What do I do from there if I want to figure out v out of s? What's that? Well, I mean, so I already did multiplying. The question is, do I want to expand that? I think, right? So I wouldn't want to multiply this guy and get a cubic or whatever, right? What I actually want to do is I'd have to do the partial fraction approach and basically undo the multiplying of this. All right. So what we typically do is I take that s squared plus omega squared. S squared plus omega squared can be written as s plus j omega times s minus j omega. If you do the math on that, you'll see that that works out. All right. So I did that. I did some manipulation here, and it becomes this. I don't want to do the mathematical messing around with it. I did a couple of things, right? I had SRC plus, I had one, just to be clear, my H of S was 1 over SRC plus 1. So what did I do here for H of S? How did I get from the thing in red here to what I wrote right here? Divided by top and bottom by RC. Why did I do that? Well, because what I'm going to try to do, it's a good question. Yeah, I don't know, because I can. I don't know. But no, there's a reason, right? Because what I'm going to do is I'm going to do this guy in terms of the partial fraction expansion, right? That's what you learned in differential equations. In partial fractions, how would I expand that thing? What would I do? How many terms would this partial fraction expand itself into? 3, right? There'd be some constant over f plus 1 over RC. Then there'd be some constant over this, plus some constant over this. All right, and that's what I'm about to do without going through all the gory details of it. All right. Why is that useful to me to make that breakdown? What's true about having the Laplace transform of a form 1 over s plus a? What do I know? What's the inverse Laplace transform of 1 over s plus a? Yeah, e to the negative at. All right. So when I do this and I go to the, basically, what I end up saying is that this thing here, right? If I break this up and use partial fractions, then I solve for K1, K2, and I called this K2 conjugate. I skipped ahead a step and said, in general, you would have called that K1, K2, and K3. I don't think that there's, if I write K2, probably the first time I've ever said this, I guess. What does conjugate mean? You should learn that with Yahoo. What's a conjugate? Yeah, so if I gave you 3 plus J2, what is its conjugate? 3 minus J2. All right, which is the same as flipping its angle. All right, it's basically, if I looked at it in the polar form. What I would find if I solved this with s minus j omega and s plus j omega like that, those two coefficients are always going to be that way, right? I don't want to derive that whole thing, but if that's the case, if I did the inverse Laplace transforming of this, I would get something of this form. All right, now I need to solve for what K1, K2, and K2 conjugate are. But I'm making the leap to say this plus this has to be what? What's that? We'll be real. E to the j omega t, e to the minus j omega t. They're not going to cancel each other. I feel Yahoo in the distance, like it's like Back to the Future with hands disappearing. Yahoo is sad somewhere in the corner, right? What if I have e to the j omega t plus e to the negative j omega t? What's going on with that? Well, so e to the j omega t plus e to the minus j omega t, what's that equal to always? E to the j omega t plus e to the negative j omega t is always equal to what? All right, what if I do this? All right, there we go. Yeah. This here, we got a winner. Cosine omega t, right? Basically, that combination of things is always equal to cosine, right? That's Euler's identity, right? It's a form of Euler's identity, right? And so it turns out that if I were to expand this further and say that this was not just, if I had K2 has got a magnitude and it's got an angle, all right? K2 conjugate would be the same magnitude, but the opposite angle, I guess, right? Maybe I should say this like this, phi and minus phi, right? Would be the way that would be written out. So if I use Euler's identity, what I would see is that this guy would basically become magnitude of K2 times 2 times cosine of omega t plus phi. All right, that's basically Euler's identity at work. Those two exponentials come back and become a cosine together. All right, we don't need to think too hard about that. Basically, what I have is a transient response, and then this thing is the steady state. Those two exponentials together is a steady state. I'm not worried about the math. All right, what I see is basically this. If I were to go through and do the partial fractions, I would find that K2 and K2 conjugate were those two things. All right, if I put those together, they become this. All right, that's kind of the important thing for me. That, looking at that expression, this part here, the e to the negative t over RC part, that's the transient, right? What happens to that guy over time? He disappears, goes away, right? This is the steady state response. It was a lot of fancy math that gets me to something we talked about 12,000 times before, right? Is to say that if I have a dynamic system, it's got a differential equation that describes the relationship between the input and the output. That differential equation solution has a transient response and a steady state response. The transient response always goes away, okay? So I get this. What does it tell me? In words, what does that mean? In terms of this transfer function idea, what is this saying? Because it says something. You guys focus on just the math of it, but what does it physically mean? The idea is what that physically means. Let's look at the way I wrote it, right? And let's go back to what we did at the beginning. So what I said was I put in a cosine input, right? That cosine input had a particular amplitude, okay? And the output is also a cosine, and it has the same frequency. What's true about its angle and what's true about its magnitude? Changed, right? And how much did it change by? Well, the angle changed by whatever the angle of the transfer function was at that particular frequency. And the magnitude changed by whatever the magnitude of that transfer function is, right? So basically what I'm doing is I plug in the magnitude of the transfer function at a particular frequency, and I use that value to figure out what the output's going to be. All right. You've been doing this when you did impedance analysis already. All right. We're just thinking of it a different way, and we're thinking of it a different way on purpose. We tend to use this when we're actually doing design as opposed to just straightforward analysis. So analysis would be if I already designed something and I asked you guys to tell me what's going to happen. Design is where I basically say, I want something to happen, and I got to figure out how I get the system to do it. And we tend to use this when we're doing the design approach, which is the reverse of what I typically ask you to do. Okay. All right. So it's an important concept. Basically, what we're saying is if I have my inputs to be a cosine of that general form, the output is basically going to be something like this. I scale the amplitude by the magnitude of the transfer function at a particular frequency. And I say that the angle is going to be shifted by whatever the angle of the transfer function is at that particular frequency. Okay. So let's look at what this means. All right. So if I had in general an h of s, in this example, what I'm going to do is if I have h of s equal to this, s, let's say it was equal to 0.1 s plus 1, like that. Okay. And all right, so that's my transfer function right there. All right, so somehow I picked my RC values, so I got that particular h of s. Okay. So I want to use this concept. And so I'm doing it in a circuit that looks like this, where I've got V of S. So I've got V, I've got R, I've got C. Okay. This is my V out. So what I have is the V out of S ends up being that H of S times V of S like that. Okay. And I apparently chose RC equals 0.1. Okay. And so what I'm going to do is I'm going to say, how about if my input to this thing is cosine 10t? Okay. Well, what I'm doing is I'm saying, all right, well, go to that transfer function. If I have a sinusoidal input, I let S equal to J omega. And I plug that into the transfer function. Oh. Yeah. All right, plug that into the transfer function. So I say H at S equal to J omega. So in this case, that is what? If I have cosine 10t, what is that? What's the omega for that input? J10. All right. So I'm saying at omega equal to 10, I want to evaluate the transfer function. So I say, all right, well, that's 1 over 0.1 times J10 plus 1, like that. Okay. So 0.1 times 10 is what? 1. So I get 1 over J plus 1. So that transfer function, that thing that's a function of S, if S is equal to J10, it's left with this. Now that thing has a magnitude and it has an angle, right? So what is how do I get the magnitude of this thing? And I wrote down here, it's 1 over the square root of 2. How did I figure that out? The magnitude of H of J10 is what? Yeah, so what would that be? What's the square root of the imaginary plus, so square root of the imaginary squared plus the real part squared? What is that? How would I write that? That's what I wanted him to say. I cornered him on that. I don't put 1 over J squared. J's not the imaginary part. Its coefficient is. All right. So thank you for taking the bait for me, Jacob. All right. If I have J squared would be -1. It's the imaginary part squared plus the real part squared. So the imaginary part squared is 1. The real part squared is 1. All right. The J is not part of the imaginary part. Okay? Everybody makes that mistake, right? So I get 1 over the square root of 2 for that. And if I do the angle, I got that was -45. How did I get that? Well, I did angle of the top minus angle of the bottom, right? The angle of 1 plus 1, sorry, J plus 1. It's the inverse tan of imaginary part over real part. The imaginary part being 1, all right? So that becomes -45 degrees. So what does that tell me? What does that tell me? Well, it tells me what the output's going to look like, right? So the output here, V of t, or V out of t, what would it be? How would I write that in this case? 1 over square root of 2 times the cosine 10t, and then what? Minus 45 degrees, right? I'm basically just applying this the sort of general formula that we derived. Okay. So it's telling me that if I built this circuit, this RC circuit, and I put cosine 10t into that circuit, and then I measured the voltage across the capacitor, the voltage across the capacitor would be smaller and it would be shifted, right? So basically what I would see is this picture right here, right? So the amplitude of the output is 0.707. If I did 1 over square root of 2, that works out to be about 0.707. And then what I see is it's got a negative 45-degree shift. The negative shift basically pushes his peak to a later time, all right? Pushes him to the right. What have I done here? Well, what I've done is I've made the output smaller, right? Effectively. I've made it smaller and I've shifted it. I'm not going to worry so much about the shift. What I'm going to think about more is the fact that I've made it smaller, all right? I'm starting to do what I call filtering here. But the important thing is really this. This is what the circuit is doing. This is how we use this thing. If I want to figure out how big the output's going to be, I say, well, what frequency is the input? And then I use the magnitude of that transfer function at that frequency to tell me how big the output's going to be. All right? You've been doing this. It's a different way of thinking of it. Okay? But we use this a lot. We're going to look at some examples between now and recitation of where we would use this. Okay? All right? So the important thing here is this is the way we think about this. This thing is a function, h of j omega is a function of frequency. All right, so it's a function. It's why we call it a transfer function, right? Basically, we say that if we put a waveform into the circuit, the amplitudes and the currents, amplitudes of the currents and voltages changes the frequency of the waveform input changes. All right, so this guy leads to the concept of what we call a filter. So we'll look at this example here. So again, we did this RC circuit a couple of times. I want to think a little bit about what I'm doing here with this thing. How did I? So I do the voltage divider analysis to get this result, right? So I've done this a couple of times now. With this particular result here, I want to think about what's going to happen for different frequencies of the input. All right. Let's say that Vn of t was a constant. Now, Vn of t being a constant, what frequency is that? 0. So omega equal to 0, right? Basically, what you're saying is if I had a constant, it's like saying Vn cosine 0t, right? What's cosine 0t? 1, right? This guy has 0 frequency. He's not varying at all, okay? So it's a DC value. We just said h of s is equal to 1 over sRC plus 1. What value of s would I put in for this to figure out what the magnitude is going to be? And just to be clear, what we're saying is that V out of t is whatever the magnitude of h of s is, right, h of j omega, times, in this case, Vn, or just keeping it more general, I guess Vn of cosine 0t, like that. All right. Help me out with this, though. What is that? What is h of j omega for this thing? S would be 0. So that, yeah, h of s would be 1, right? If I plug in s equal to 0, I have 1 over 1 or 1. So what's that mean about V out? V out and Vn are equal to each other. Let's see if we can make some intuitive sense of that, right? So if I'm looking at this thing right here, I got R and C in series with each other. In DC steady state, that's what this is, right? DC steady state. In DC steady state, what do you guys always say that the capacitor is? An open, right? If the capacitor was an open, what would V in and V out be? Be equal to each other, all right? So that you've known that since circuits 1, effectively, right? So the other way I can think about this is if I think about the impedance of the capacitor is 1 over SC. If S is equal to 0, what is that equal to? Infinity, which means that this is an open circuit. And so I've got an open right here, so that means that V in and V out have to be equal to each other. So there's a couple of different ways of thinking about that, but that basically tells me that V out in this particular case would be just simply V in. All right, now I want to think about what happens if the frequency becomes really high. So let's say I put an AC waveform in and I said to myself, H of S is 1 over SRC plus 1. And if I said to myself, I want to figure out the magnitude of that thing. If I plug in this guy, I plug in S equal to J omega, right? And then I get the magnitude of that thing, right? What would the magnitude of that be? Well, let's not even think about for a second. Oh boy. Let's not even think about for a second. Thinking about the number for the frequency. If I just said this guy was equal to, hang on, don't jump ahead. Let me just say it's H of messing with me. All right. All right. We're gonna do this. We'll go back. We're almost done for here today anyway. Okay. Oh, wrong one. All right, we may all right. We're gonna pick up with this in recitation.